Please welcome the panel to the
It's not open
stage.
with that.
Ta-da! We're here.
You made it.
Thank you.
We're SRO, baby. So, can I start? Are we good to go? Excellent. Hi, everybody. Thank you for coming. You picked the perfect panel. We're going to be the best. So you've made the right choice. I'm Sue Karlin. I write about science and technology for Fast Company. And these are my rock star panelists. Any one of them could talk for an hour. But we're going to get as much into this panel as possible. So I'm going to set the stage first. There has been a seismic shift in how we innovate. Small groups of researchers have given way to moonshot goals that take a global village to pull off. Think of the Wright brothers versus Apollo, Jonas Salk's polio vaccine versus the Human Genome Project. So now we're expanding that strategy towards loftier goals and unexpected applications. So our panelists are at the forefront of this expanded approach, and they're going to reveal how they've applied this thinking to technology, targeted medicine, and financing. So first of all, why has this happened? Who wants to go first?
You're looking at me?
And I'm looking at anyone. You know, why has this seismic shift happened?
I think that I speak from a medical perspective, but we're all working much more collaboratively and at scale. I think that the vision across from a medical perspective and a medical research perspective is that you have to really look at bringing big data together across state borders, across international borders, because the only way we're going to make a seismic shift in everything is by really bringing the best minds together to solve a specific problem.
To jump in, so I'm Kara Ultimus. I lead the Milken Institute Science Philanthropy Accelerator for research and collaboration, and we work across a number of different scientific and medical ecosystems to develop targeted solutions in partnership with philanthropies. And that has given us a really unique perspective of seeing where science funding and philanthropy has been and what the current needs are and where it's going. And so one of the, just riffing on this change and what's driving it, we've seen decades, a century really, of science innovating kind of in a one-off, investigator-initiated model, and that is excellent for the planting of 1,000 seeds. You know, getting the million ideas out there, getting the start of discovery. But when we see the opportunity to dramatically shift science in the direction of actually curing a disease, getting to the moon, solving a problem, that is no longer a one-person, one-lab problem. That becomes an ecosystem-level problem that requires expertise across many domains. And so it's in these areas that we have enough insight to know that there's a place to go, but not enough coordination yet, that you have to actually change your model. And that means changing the structure of how individuals come together, changing the structure of funding, and changing your incentives and expectations. And that is, we're in this messy middle space that science is learning how to do that well, particularly in biology, and I think very much following what's happened in physics and what we learned from NASA in space to be able to get there and think about how to solve those problems.
Yeah, it's not only sharing risk, not only sharing information, but also sharing risk.
Absolutely.
Yeah.
Yeah.
Allowed to chat?
I would. I'd like to add that it's also timing, right? And so, what we've seen over the course of history. Steve Altimus, by the way, Intuitive Machines, and we just lunar landing company, cislunar economy, developing kind of company.
You're being very humble. His company just landed the first private and American lunar lander on the moon since the Apollo
52
era.
years.
Yeah.
First time in 52 years. And what brought that about? I think, was timing. So if you think back on the development of space programs, they've been influenced by the Cold War, where you had the Soviet Union and the United States building monolithic programs to go to the moon and show technical prowess. So then you saw an age of collaboration in space, where the timing was right, where you built the NASA and 110 countries built the International Space Station. And each country got a module or a piece, and then the interfaces were strictly defined, where it wasn't exactly fully collaborative, but what it was an approach to, you take this piece, I'll take this piece, and you'll build an International Space Station. And now what we're seeing is by the change in procurement, the change in the way that our government buys goods and services has allowed for the commercial sector to lead and be part of this, where it's no longer just sovereign governments. And now we can leverage, at least in the U.S. economy, we can leverage the ingenuity and the innovation that comes out of private investment and it comes out of commercial companies and tag that with the federal dollar to move faster and further. And I think that has been transformational for us in the United States, and it will be our competitive edge in the space race moving forward.
And then Josh.
So Josh Denny, I'm CEO of the All of Us Research Program, which is part of the National Institutes of Health, U.S., and seeks to enroll at least 1 million people across the United States, representing all backgrounds, diversity in many perspectives, to help advance medical breakthroughs that are relevant to all populations. And I think the transformation that we saw with, as Catherine noted, big science projects. So you think about the Human Genome Project, which could be hearkened to a map without labels, maybe. We understood and we certainly knew where all the roads were maybe with the Human Genome Project, but there were the understanding of the impact and maybe the cities and states or the impact on disease was needed. And so projects like that bring together people, lots of diverse genomes like ours, that also include health information and allow them to answer surveys and bring in new technologies are the kinds of things I think that are needed to create a large platform for people to discover. So it's the scale of science that enables those million projects to bloom on top of it, but without large concerted efforts, with huge numbers, you're not going to get to unravel these vexing problems. And
then Reed, what do you
Absolutely.
have to add to it?
Well, it's a pleasure to be here. I'm Reed Jobs. I'm the founder and I'm the lead of Yosemite, which is a venture capital group in San Francisco, and we only really invest in companies that are really tackling cancer and all types of cancer-related therapies. So I'm sure we'll talk a bit about that. But from, I guess, my vantage point, what we're seeing now is really the fruits of, I'd say, roughly 4 generations of compounding research that have happened, particularly in oncology. And if you think about it, people who actually discovered the structure of the human genome, one of them is still alive today, still with us. So this is very much something that's still within human lifespans right now. Yet the amount of new technological modalities that we've found in the last, say, 20 years have eclipsed anything else in human history. I mean, how many of us have mRNA vaccines in us right now, which is completely a new discovery? Things like cell therapy, gene therapy, all of these are really in their springtime of their life cycles. All the people who discovered those are still alive and actually in their prime. So we're seeing sort of this kind of layer upon layer that we've built over the last, say, 70-ish years or so, really getting into new areas right now. And all these new modalities are kind of matrixing against each other. So the potentials right now, at least for the oncology space, are immensely interesting.
And I was going to also add to that is that there had to be an advent of technology to facilitate all that, of supercomputing, AI, modeling, things like that, I think couldn't have enabled this shift as well. So was that something you'd agree with?
Yeah, I think at least for the space program, if you recall the Apollo program, there was no computer. They were people at the time. And it was MIT who actually came up with the computer that allowed us to fly to the vicinity of the moon and land on the moon. Today, as a business in the United States, there's a supply chain that we can leverage all of the dollars, the trillions of dollars of research that have gone into microcomputing, high energy density batteries, miniaturization of electronics. All of that has enabled us to lower the cost of access to space, which is done primarily by SpaceX and other companies, but actually to lower the cost of access to the moon, where it was inconceivable to think that it wouldn't cost 4% of the gross domestic product to land on the moon. I talked to an investor at one time, and he's like, doesn't it cost like $1 trillion to go to the moon? Well, now we can go to the moon at a price point of roughly $100 million a mission. That's insane. It's an incredible advancement due to all of the R&D that has gone into the economy over the years to advance the technology.
Did I just cut somebody off just now?
No.
Okay. So kind of riffing off this collaborative effort, and it's not just private and public money. It's not just government, private industry, but you're also doing novel financing and community outreach. And so, I wanted to focus on that a little bit. I want to start with Steve because he did a figurative and a literal moonshot. So let's jumpstart with you. How does a tiny startup end up kickstarting a lunar economy?
Yeah.
In 4 sentences or less.
Yeah, I can't speak that quickly. What was interesting, I spoke about timing. And in 2018, the executive branch, the administration, the National Security Council and National Space Council declared the moon of strategic interest. And when that happens, the U.S. is compelled to spend money on advancing the moon, the lunar economy. In this case, sustained human presence on the moon. And so they looked at NASA as the point of the spear, as this arm of soft power in the United States that could move us out into the solar system, out towards the moon, in a significant way using, from the Office of Commercial Spaceflight, non-traditional procurements. And so what they said was, let's go start this commercial lunar payload service program where we as a government will no longer build the infrastructure, but we're going to rely on the U.S. economy and commercial companies to get there any way they can. They gave us a handful of payloads and said, go send these to the moon, go get the data back from these payloads and bring that data back to us. And if you can do it, fixed price for about $100 million in the time it takes to get an undergraduate degree, you win.
And the cost of getting an undergraduate.
A lot of gray hairs later, right? But they started at the beginning with an idea of driving the price point of landing on the moon as low as it could possibly go.
So you're seeing the markets.
Exactly. So by doing that from the start, instead of building these multi-decadal programs that cost billions and billions of dollars that span 10, 15, 20 years, let's start with how do you do it as cheaply as you can. And I think that has just landing on the moon in that price point, in that amount of time, has broken so many economic barriers and so many technical barriers. And that's what's unique about the United States and unique about the U.S. economy in the way they innovate. And I think that was the recipe that allowed us to be successful.
And even more remarkable is that you, while you had backgrounds in the space industry, you kind of formed your own company. It wasn't like you were Lockheed Martin and said, hey, we want to do this. It was like you were a group of guys who knew a lot, but still just a group of guys said, we can do this.
And part of that was, just to add on, is how do you do something that has never been done before? Well, I'll tell you the way you don't do it is you don't do it like everybody else. You have to think differently. And so there was a lot of people that came out of traditional aerospace that says it can't be done, it can't be done. But if you think about, well, what can be done? Where do you take the best of human spaceflight or the best of engineering? And you throw away everything else. And then you say, I will not be deterred. Any barrier I come up with, I will figure out a way to solve it. And you put that culture into your company. And that company can't say no. It has to get through each one of those challenges. And you have to do it differently. There was a number of people who came into the company that didn't understand that. Yet we had to find those people who were willing to think about the problem differently and to put their brain power to work to solve these intractable problems. One example was that we had to, we built an engine, liquid oxygen, liquid methane, cryogenic propulsion system using advanced manufacturing 3D printing. We printed it out of high nickel steel. We printed the injector in 5 days. We post-processed it in another 5 days, and then we put it on the back of a truck and fired it as an engine down on a taxiway at Ellington Airport. That kind of innovation to move rapidly, we printed some 40 injectors and built our own engine for the first engine to fly in space as a liquid oxygen, liquid methane engine.
It was like an engine on a truck.
Engine on a truck, like an afterburner.
It really was. Yeah,
Right.
yeah.
So those kind of innovations, resulted in, literally hundreds of innovations and inventions that came out of the company, just trying to solve the problem that's in front of you and not give up.
Linking this to some of the biomedical work and philanthropy driving a unique source, a lot of times you see private foundations and philanthropists focused on what does it mean to be a philanthropist and to be a source of funding that is not going to be the dominant source in a field typically. Typically it's government and private investment. And so how, as maybe the minority investor in an area, are you able to drive dramatic innovation? And there's a lot of commonalities here. And one, you see a drive to think about how to bring in federal dollars, how to attract NIH to an area. But I think where we've seen some really impactful is how to drive private dollars to come on the back. And a story that feels very aligned is in Alzheimer's. So if we go back 5 years, we were seeing almost all companies move out of neurodegenerative research, pulling failures of clinical trial after failure of clinical trial. And the news was, just showing the dissolution of the neuro programs within these companies. We had a philanthropist at the time that was asking, how do we get involved? How do we drive further innovation? And they were thinking about new drugs, new curative therapies. And as we looked at it, we said the reason companies are leaving is the clinical trials are failing because they can't diagnose Alzheimer's. What's needed is a deployable diagnostic tool, not just the drugs, but actually the ability to determine. It was like 30% of control groups actually had Alzheimer's, and 30% of the population group did not have Alzheimer's. So it was that much of a messy population. And there was a scientific finding at the time that you could detect the presence of Alzheimer's in CSF, but that's not very useful. By prioritizing that, a group of philanthropists came together and prioritized the development of that in a blood-based biomarker. 5 years later, anyone can get a blood test and detect Alzheimer's or not. And now 5 years later, we see a change in the marketplace where companies are coming back in and actually asking how to be more involved, how to put therapeutics back in trial. And so it's a place that you have to think about what is the best way to engage with whatever dollars you have to actually drive a change in the marketplace, whether that's federal investment or private investment.
So identifying the roadblock.
Yep.
And
being willing to take the risk on it, which is another.
And then having that solution then redrive the market, but in a slightly different way.
Right.
What makes a good investment? And I'm going to bring Reed into the conversation. What do you look for, to create a moonshot or to invest your dollars?
Well, I am a venture capitalist, so that's kind of important for my job. So in terms of what we're really looking for is, I'd say sort of one of three things. First of all, if it's a totally new modality, we love that. And every once in a lot of people think they have one, and usually they're optimistic. But if occasionally there's a few new areas that we see coming. One, for instance, would be epigenetic gene editing was an area where we saw a lot of advancements with CRISPR, with basic gene editing. But if you actually look at that, which is a fantastic technology, it it has a few problems with it. It can't really replace genes very well. When it cuts things, there are occasional, off-target mutations that happen, which you really want to avoid. But by going after, say, like the methylatory markers, which actually aren't part of the genome, but they regulate a lot of it, you can have a much more discrete therapeutic index. So that was one area that we kind of saw early on as being a real true platform. So I'd say one is just a very, very new kind of white canvas area. Is something that we love. We love being the first there.
They're not necessarily hitting the obvious, but like the cause, like side causes.
Sure. Yeah. Or you can a little bit you could say is seeing current gaps of therapies and what if you kind of play the tape out is going to fill that in the long term. Second thing is there's a lot of companies in this space, unfortunately, that fail. Yet many of them, at least in the biotech sector, fail for very bad reasons. Not science reasons, because they timed the market wrong, because the CEO couldn't raise money, because there was a disagreement between the scientific founders and they kind of broke up. It's very high school. But this kind of thing happens all the time. And it's really important to look at a lot of these areas because oftentimes there's really interesting assets that sort of get overlooked for the wrong reasons. So that's another area that I'd say that's a bit of a generic answer, but there's frankly a lot of this in the industry. Lastly is just putting all this aside and betting on people. Because at the end of the day, we've really invested in a lot of companies and lost money with great areas that were totally right, but the people screwed it up. And I really don't love that. But, we've worked with a lot of really successful entrepreneurs and scientists kind of repeatedly. We always like to see new areas and are exceptionally meritocratic about how we source things. But yeah, at the end of the day, if we can really bet with someone who we know and we trust, that always is heavily weighted.
And I wanted to rope in Josh and Catherine. You've been very patient waiting. You guys are two sides of the same coin in terms of collating and sharing data. Josh is reaching out to the public to create a DNA database. And then Catherine, you're reaching out to other countries for shared data. So talk about your efforts and then why medical research can no longer be siloed.
Well, speaking from the U.S. perspective, I see a common theme here. Even if you think about, Steve, some of your problems that you're looking to solve, it's very different, obviously, if you think about medicine. But what do you need to actually go to change the health trajectory for populations across all diseases, all medications, and the populations that are left out, where we have huge gaps in health equity? And part of that is, what problems are in your way and how can you solve them? It's the same thing, and we're not getting neurodegenerative disease development like we want, then maybe it's because we don't have a good biomarker for Alzheimer's disease. So one of those big stumbling blocks for the U.S. is our fragmented healthcare system, electronic health records across many different vendors, standards, things like that. And so if we wanted to build a national population, a cohort for the United States, that can be a resource for discovery for the world, we had to figure out a way that those data could be come together and shared and harmonized, and just assume that we can do it. Assume that if you get 1 million genomes, that you can figure out the math to be able to compute efficiently on top of it, because you need lots of genomes and lots of human variation to understand the impact of genetic variation on disease and health and better screening modalities and all these kinds of things. And so as you solve maybe one of those problems, then there's another way you can do it, and you can keep iterating, trying to drive costs down is important, and then it becomes something that's useful. When COVID happened, the fact that we in this country had already shown that and pushed through with lots of healthcare systems to share electronic health record data in a common format was something that was turned around and rapidly redeployed to create virtual data sets to help answer questions around COVID. And it's becoming more and more common as we think about it. And so that's a U.S. perspective as one part of this problem. And it can also be applied internationally, because we can only solve the problems of scale that we can internationally. And so even though I'm here representing the US-based All of Us research program, we believe it's important that international researchers use the resource for discovery. We really believe strongly in the partnership across countries. Science knows no boundaries. That's a Pasteur quote, I believe. And we have to work together, because 1 million's a lot, but it's not enough. We estimate we can look at 400 plus diseases with 1 million people with adequate sample size for genomes and environmental influences. We really need to go across all the kinds of environmental exposures, genetic variation, diets, things like that across the world. And so that's where things like Global Alliance comes in.
And Catherine, I was going to ask about how do you take competing entities, medical entities, competing countries, and get them to share all of this data?
As Josh has said, you need the data of millions of people to be able to, from a genetic perspective, accurately predict for one individual. And so it's been a real journey that's very parallel in terms of what you've been talking about with the moonshot, and has paralleled the increase in technology. So your genome is your entire recipe book. It's equivalent to 1,000 copies of War and Peace, which if you piled them one on top of the other is an 18-story building. Huge amount of information. Josh mentioned the Human Genome Project. That brought countries together around the world and laboratories around the world to say, how do we sequence this? And it took 13 years and it cost $3 billion to do. Now, with the acceleration of bioinformatics, with compute technology, with sequencing technology, I think the world record now is turning around a whole genome in around 18 hours. But we regularly now, in clinical practice, are able to provide a result in 3 days. So that's 13 years to 3 days to be able to provide that degree of specific genomic information. So, in actual fact, the Francis Collins, who led the Human Genome Project, brought together a group in 2013 and said the next problem we have to face internationally is how we aggregate and share all of these human recipes so that we can identify what's normal, what's abnormal, what's associated with disease. And to give quite a specific example, if you're a person that is diagnosed as carrying an alteration in your breast cancer gene, that's quite a good and common, unfortunately, example. If you've got that spelling mistake, you want to know, is that just a normal variation? Of course, we're all different. Or is that associated with breast cancer? If it's associated with breast cancer, does that happen 95% of the time or 5% of the time? Because on that basis, your doctor is going to make a decision as to whether he recommends that you have bilateral mastectomy, which is, quite a, it's quite a major intervention. So Francis Collins brought together a group of people and saying, we need to be sharing our data internationally. And that led to the formation of the Global Alliance for Genomics and Health that Josh has mentioned, of which I'm vice chair. And that's bringing together over 100 countries that are focused on how we safely and responsibly share both clinical and genomic data across country borders. And there are a number of different barriers that we have to overcome, but we are doing that. And it just means that we can establish, and we have established, a collaborative international community that's working together to solve these issues at scale.
Do you have any, I'm putting you on the spot, sorry, any interesting anecdotes about maybe a barrier that resulted from either competition or a cultural methodology that you had to overcome and how you did it?
I think the first thing that we need to overcome, which I think we'd all appreciate, is governmental borders and security and ethics. Sharing data in the cloud, there is rules in place where you have to keep data, medical data, personal, private, clinical data, within the cloud of your own country. So how do we overcome that? And the approach that we've taken globally is to look at how we federate all of these different the different cloud structures, for example, so that instead of making a whole mass of data that's sort of sitting in one place. We have the data sitting where it's generated, but we bring the analysis to the data. So federation, I think, is and developing the software, the approaches, the informatics to make that easy is what's now making data interoperable internationally. The goal of this is, how do we end up with Google Genome? How do we, to pick up our phone, if you're diagnosed or found to have specific changes within your genetic code in your recipe book, how can you then plug in and ping around all of the different data around the world to get an answer that's based on evidence that's specific for you?
Okay. One of the other things that I was seeing in my research is that moonshots like to either look, in the past you'd have surprise applications that you weren't expecting from the technology you developed, but now I think that you are kind of looking in advance. Like, we're developing this technology, where else can we apply it? And I think that seems to be a relatively new way of approaching these projects. And can you talk a little bit about that? Is that something that, Reed, you look for in an investment, or Kara, that you look for when you're deciding how to guide various companies? And I know that NASA's very big on that too. So I don't know who wants to jump in first about talking about that.
Well, I'll talk a little bit about it in terms of, generally, as a business, and the venture capitalists will say this, it's focus, focus, focus on what your business is. And so trying to find adjacent applications that are outside your main focus area could be detrimental to your business, right? But to the degree to which you can pull in technologies or applications that would help your business and your primary focus, I think, is the right way to think about it. So, for example, we take a tremendous amount of data from the Lunar Reconnaissance Orbiter, which has been circling the globe for, or the moon for 20 years, generating petabytes and petabytes of data. So now what we want to think about is, how do you do landing site assessment? How do you do autonomous driving, path planning, and things like that? And so we went, of all places, to University of Texas Medical Branch in Galveston, who created a Google Cloud for patient records, who actually for cancer treatment, and then took that database, which is a simple structure that businesses use to create cloud platforms, but then applied AI algorithms to sort through that breast cancer data. So using those consultants that set that up for UTMB could turn around and talk to us as a space company and say, here's how you organize that Lunar Reconnaissance Orbiter data so that you could be the world-class owners of data around the moon, and you could parse it to get to site selection for NASA future missions, for anybody that wants to fly to the moon. So we're using cancer-related research and data platforms back to referencing the mountain of data that we need to sort through to land on the moon.
I didn't realize there was so much cross-pollination going on. But now, in turn, your company's also developed quite a number of patents, too, that you then can apply to other sectors.
Yes. However, again, the focus has to be on where you're going as a business, and not get distracted by all of the terrestrial applications that you could do as a result of having flown to the moon. So Apollo had all these intellectual property and patent relatable items, inventions that the taxpayer paid for, and they went out into the world. As a business, we have to consider that and say, is that appropriate that we give away? What is open source? What do you give away? And what do you keep as proprietary? And what do you share? Is an interesting thing that keep your focus. And that's the fact of the commercial sector. That's a reality of the commercial sector. What gives you the competitive edge, right? What keeps you moving forward in the business? So That's not the answer you were looking for, but that's kind of how business has to work.
It's not the SATs.
Yeah, right.
All answers are correct.
Are correct.
Relatedly, one of the things that we are looking for, and that I think we have a special place, is popping up in one place that are easy or make a lot of sense to move into another. So one that consistently shows up at the moment, but it's a broader understanding of science and biology, is the impact of the immune system and immune function across a number of disease areas, and how innovations in both immune therapies and immune markers and understanding are informing how we understand neurodegenerative disease, mental health disorders, chronic illnesses, child and development disorders, and it's that kind of innovation that is in any one pocket that you can then apply more broadly across and understand human and disease biology more holistically across the population.
And Reed, when you're looking at investments, do you look for other applications that could come out of an industry, or are you just strictly focused on what their primary?
Oh, hell yeah. No, absolutely. Now
Is that a yes to which question? It was an or question.
We look with a very critical eye towards many other transferable applications. And why I say critical is because, a lot of people will pitch you that, my technology could be applied to all, these 2,300 things. And, usually that's an exaggeration. So more often than not, you don't want to be underwriting someone's kind of worse tertiary program. However, what Kara says is absolutely correct. So what we're seeing right now is some really interesting biological transferabilities in a few areas. The one that I see the most, because I work in cancer, is exactly what she said, which is applying a lot of really interesting immunotherapy technologies for autoimmune diseases. Because at the end of the day, you're kind of doing the same thing. The way that immunotherapists look at cancer is a disease of immune dysregulation, meaning that your immune system is supposed to kill not self, and it's not doing that. And in many ways, you could see autoimmune disease as kind of the other side of that coin, where it's actually, mistakenly killing you, thinking that you are something foreign, and obviously that's a horrible mistake as well. So by being able to kind of make a dial on the immune system, you can both go into cancer and into autoimmune diseases. Another really interesting area that we're seeing that's more nascent, kind of bubbling up, is a lot of gene therapy research being applied for climate work, actually. Because, if you can, say, perturb someone's microbiome, you could do the same with soil. And in fact, you're actually seeing it piloted there because, regulatorily, it's a lot easier to go into plants than it is into people. So there's a lot of transferability there that's already been happening in ways that we think are very real. So yes, we look at that a lot, and we're kind of seeing more and more of that, which is super, super exciting.
And I wanted to ask Josh, one of the things that you're finding with the All of Us project is that you're able to answer more elusive kinds of health questions that you weren't able to answer before. It sounds like these kinds of larger initiatives are enabling people to target kind of impossible solutions. And I was wondering if you could talk a little bit about that.
Yeah, I think where cohorts used to be established was we're going to look at cardiovascular disease or cancer. We're going to pick a topic, osteoporosis, and look over time. And where we've moved really internationally, I would argue, is towards more disease-neutral, large resource cohorts that you can ask many questions. And then you actually end up discovering a population like all of us where people can just basically raise their hand and enroll anywhere from the United States. Collects people from all sorts of different reasons. And we find that people with rare disease are overrepresented in the population. They are maybe more motivated to go in and get a sequence, which probably makes sense. And in fact, we actually return information to participants. We return genetic information of risk of hereditary cancer syndromes, cardiovascular disease, things that we can do something about, such as the breast cancer gene that Catherine was referencing, and certain hereditary cancer syndromes that you can do something about. And then there's a cycle there because we have the population, we have a diverse population that's enrolled, and we have their clinical information, we're able to get things like Fitbit and other kinds of information as well. They get surveys, and we're able to see genetic influences that put one at risk or maybe protect for disease. And in some cases, we already see some evidence now of that, where something that we have shown really for the first time in our cohort can then be fodder for us, implementing that and returning that to participants. And by doing so, it becomes part of something that can happen in the clinical environment. And by having what I hope will soon be, 1 million participants across the country, starting to take those kinds of genetic reports to their physicians, maybe we will start to do something that we've been unsuccessful at, I think, in terms of advancing precision medicine as they bring that into the office. So, and that doesn't even talk about all the great ideas, the plethora of researchers come into and ask questions of, even down to high school students and people at under-resourced institutions, because they can use our data cloud and our resources to ask the questions. So I think you get great ideas you never would have thought of that can cross disease boundaries, that can cross to modalities. I love the analogy of autoimmune disease and cancer, and you even find people are showing that somatic variation, so like the same kind of variation that you see in cancer, where the genome that you're born with isn't necessarily, some cells have a different genome and mutation there, can look like autoimmune disease. And so there's a recent syndrome that was discovered in that vein as well. So I think there's lots of emergent discovery. If you create a platform, make it accessible, get lots of data that might be just in case instead of always driven by a hypothesis, and then have lots of people able to ask those questions.
We have a few questions coming down the pike, and some of them are really interesting. So I wanted to ask you they're coming from the Ethernet, the human cloud. So the first one was like talking about aligning the breakthroughs that you're getting through moonshots with policies. So for example, you've got the person who wrote this question said, thinking of the cancer moonshot being laudable, yet smoking being the leading cause of cancer, and the last FDA-approved device for smoking cessation was 20 years ago. So how do you get those two arenas aligned? What, Reed is shaking his head. You don't?
It's not the leading cause of cancer anymore, actually. It's obesity now. 2 years ago, it overtook smoking. Seriously, we have an absolute epidemic of obesity in the U.S., and like smoking, it's a pan-cancer risk. So that's the new data.
Oh, that's really interesting. Okay, so then using that, like how do you get policies in place to, if you're finding out a cause for something, then how do you work with the government to get policies in place to help your findings? Because if you just find something and find a treatment and people aren't doing it, then it's sort of
I have
useless.
a case study I'm really excited about on this.
Okay.
So we, a couple of years ago, started working on an initiative for bipolar disorder. So it is a disease-specific initiative. It's called BD Squared, and that field has been dramatically underfunded. And there's not an understanding of the heterogeneity or trajectory of individuals living with bipolar. As we were working with the field and some philanthropists to develop a cohort, the question came up, how do these findings ultimately change clinical practice? And when we look at across cohorts, the answer is they do over the long term, but they don't in the short term. And further, when we looked at the bipolar clinical practice in settings and environment, what we found was that bipolar is treated dramatically differently, not just around the globe, but East Coast, West Coast, whether or not you're prescribed lithium or antipsychotics or antidepressants, and that affects outcomes in the range of by 100%, how well a person is doing or not. And so we realized that not only did we need to drive science forward, but we had to change the system and the culture. We needed to bring science and clinical practice and the culture together under one single initiative to actually drive the change we were looking to change. So we created kind of custom built what this initiative was going to look like, so that we were designing both the cohort inside of a change in clinical practice called a learning health system that is actively learning from the data it's getting. All clinical record and all scientific data going into the same platform with analysis done in real time, looking for the good, what works well and what doesn't, so clinicians and participants can learn from that data and update it today, rather than waiting for 20 years or 10 years to do so. So it's not at the federal policy level, but it's at the provider level, which is where that is functionally happening.
And I've got a point that I think is quite relevant in working with governments in what's a disruptive technology such as genomics, is doing the health economic analysis to demonstrate clinical utility and cost effectiveness. And that's also something that we can share that data internationally. But as an example, as genomics was starting to come into clinical practice, we did a study that demonstrated if you had traditional approach to diagnosis with kids with quite severe genetic or syndromes that cause intellectual and physical disability, that the diagnostic rate at that time was around 10 to 11%, and the cost per diagnosis in terms of all of the investigations was $26,000 per diagnosis. If you add in a genomic test, the diagnostic rate increased, and this is back about in the olden days, like in 2015, that the diagnostic rate in the same 100 children lifted from 11% to 55%, and the cost per diagnosis went from $24,000 to $6,000. So 5 times the diagnostic rate at a quarter of the cost. That then turns governments' heads, and we have a national health system, so it led to genomics becoming nationally available and equitably to all children that were presenting with these types of disorders. It also influences in the US whether an insurance company will cover the cost. So there is that element, and I think most importantly, if we go back to what's more expensive, which is doing that 3-day turnaround time in kids in intensive care units, then that early diagnosis often allows an early intervention that's going to prevent those children from becoming intellectually impaired. So epilepsy is a genetic disorder, which it wasn't when I trained in neurology, but it's regarded, it is now known that it's is a genetic or inherited disorder. And by rapid diagnosis, when the children are having their first seizures, rather than the trial and error that tends to happen in therapies, targeted therapies can stop their seizures so that the kids are seizure-free and develop normally. So I would say that the promise from a genomic medicine perspective is that we can change the focus of the health system from waiting for diseases to happen and then trying to treat it, which is expensive and ineffective, to prevention and early intervention. And it comes in with smoking, with obesity. The challenge is, how do you stop people smoking and how do you stop people eating?
And are you getting more a pushback from the insurance companies or for socialized medicine from governments?
Well, in Australia we have a national healthcare system, and I would say the same in England with Genomics England, government funded in terms of developing the genomics pillar of the NIH. But I'd ask Josh to answer that. But certainly I've been increasingly impressed by the private health insurers covering the costs of the diagnostics, but then there's sometimes very expensive therapies that are life-changing because they're preventing lifelong disability.
Well, the example that comes to mind is I recently read an article about a new blood test for certain types of cancers. And I thought, wow, what an amazing thing, except insurance doesn't cover it, so you'd have to pay out of pocket. And I was wondering if that is part of your battle of pushing forward research, but then having insurance companies say, that's great, but we're not going to pay for it.
Obviously, there's a nature of this which varies, obviously, by what country you're in. If you think about these different perspectives, Catherine highlights the need for more economic evaluations. And a lot of where we start as clinician researchers has been discovery of some of the effects. But you can see ways in which they quickly pay off and some of that translation of story. And you've already seen a shift in moving towards earlier whole exome or whole genome sequencing on individuals with undiagnosed disease in certain scenarios, sort of intellectual developmental delays and things like that. And that yields greater diagnostic rates. We've seen studies that look similar to unexplained kidney disease, where you find a 10% diagnostic rate of something that may have an influence. And people are looking at this in ICU settings and other kinds of scenarios where we are finding things we didn't expect that may make a difference. And I'll just give one anecdote of a patient that we saw back in my clinical days that did not respond, had a heart attack, got typical therapy, and over the course of about 11 months had 9 stents placed and 5 interventions, and it turned out that there's a pretty well established at that now, especially, that there's a drug genome interaction there, and for up to 20-25% of the population, you can target that much better, those therapies, using genetics. And genetics are the kind of thing that you can read once and use many times. And so if you think about the power of having that in electronic health record, you could start to make a lot of those scenarios from cancer screening syndromes to more intelligent screening to cardiovascular disease and preventable, potentially very life-threatening conditions to better use of medications, sometimes which saves you money. You can use the old medication, perhaps for a lot of people, and then scale to more expensive novel therapies when your genetics tells you need to. And we are early in the days of understanding a lot of these kinds of stories, but there are a lot of stories that are pretty well understood that we can improve health, improve screening, avert disease by a lot of these kinds of stories. And hopefully that builds up to compelling stories for insurers.
Now, I knew this question was going to come up. What is the promise and peril of AI with your collective work? I think we should cue the Jaws music in here now.
We all, I'm sure, have opinions on this. Lots of promise, and we have to use the power carefully. And this is actually one of the real, I think, driver use case and excitement for the future behind programs like All of Us. It's a huge data set. We have really tried to represent a diverse population. Nearly half of our population is diverse by race and ethnic self-declaration, but also disability, rural, sexual gender minorities, just a lot division across that. Because if you don't have diversity of representation, then of course we all know you can train an algorithm that tells you something that you don't want it to tell you or isn't applicable. And one brief example, one of the first papers published out of our platform looked at an algorithm to prevent who would need surgery for glaucoma. And it used a bunch of features. It was trained at one particular site on one electronic health record. And then when they applied it to our data set, it didn't work at all. It was like flipping a coin. It had no predictive capability. Because one of those other things that's important is having lots of different electronic health record vendors in lots of different parts of the country, and all those things across in your model. And building a model off of a diverse data set produced a model that performed very well with high discriminatory accuracy. And so I think that's just one of many examples we could point to of lots of other use cases, and we'll come up with much more powerful examples for AI, I think, than whether someone might need surgery or not. But I think there's a real future, and I'm excited about the future of incorporating that. We just have to make sure the underlying data helps us support, and that we are careful about how we apply.
Building on that, we have a couple projects, initiatives at the moment that are looking at how to drive further innovation using AI in health and science. And a couple of things that I think are we need to keep front and center is tons of promise. And AI is not new in application in health and science. I'd say maybe even started there in terms of how far we've pushed. But the data is not equal across how we understand human health. And so in an area like oncology, the data sets are vast, they're deep, they go on and on we have more than a decade of data in a lot of areas. And if we compare that to the data in serious mental illness, it's almost absent. And so we have to be thinking about how are we driving discovery across different types of data, not just health records, but actual areas that we can use to drive innovation using AI, and then touched on in different populations. And so who is represented in data sets starts to matter a lot when you are then asking, how do we use the power of big data? And so genetics is a big area that we have seen a vast majority of the genetic sequences that we have are on individuals of European descent, and there are major initiatives working now to change the makeup of the available genetic data, but that is reflected in health record data, that's reflected in brain bank data, and so as we look across, we need to be thinking about how do we both develop the tools and elevate the data, both disease type and individuals that are contributing to it, so that we are driving the kinds of change we want to and able to apply algorithms and methodologies across.
We have about 5 minutes left, so I wanted to make sure I could get your 5-year projections in for your company, or 10-year, or 3 months, whatever you feel comfortable talking about. But are you able to extrapolate what you're doing now into the future? Do you want to, Yeah,
I'll lead off there. It's certainly exciting. Where you start in 2018, when I talked about the National Security Council's strategic directive, there were 0 lunar landers or lunar programs being built in the United States, or essentially around the world with the exception of China and India. Today, in the United States alone, there's over a dozen lunar landers being built today. And there's a whole group of scientists and engineers working on payloads that need to go to the moon for science and discovery. So what we're able to do is, as a company, think about the idea of delivery service to land on the moon. We think about then command and control, which is communications, navigation in and around the moon, and how you might set that infrastructure up and offer that as a service, so that you can produce surface operations. And so we've become a company that can actually fly and execute missions to the moon, not just design space systems, a lunar lander, for example. There's a lot of NASA requests in the past have been, give me a spacesuit, give me a lunar lander, give me a lunar terrain vehicle, give me a rocket, give me a spacecraft.
Lunar Starbucks.
Now we can create a whole cislunar economy, and I contend that commercial companies can create a blueprint for commercializing celestial space, and that's where I see it's going as a company moving forward.
Okay, interesting. We'll show you how to do it. We're not only doing it, but we'll show you how to do it.
That's right.
Okay. Kara.
In science philanthropy, we see just a tremendous growth and engagement of science funders generally in the ecosystem. As I look forward, I think we continue to see the need and the momentum around bigger science, targeted science, collaborative science. And we think about that as a model, but I think that's really, it's a culture, it's a mind shift. It is a way in which we are promoting and doing science and how we build expectations, incentives, and funding around that. Right now, I see a lot of thinking about how do we bring those mindsets to science. As I look forward, I think we're going to see more and more of that same set of expectations on the funders themselves. how are we creating partnerships across funders, across funding types, and then carrying those expectations into the actual scientific spaces. And that becomes all the more tractable, because then if we're talking about data sharing, if we're talking about collaborative engagement, that becomes even easier as you mirror those same principles in the way and in the funding structures as you are as on the scientific structures.
Okay, next victim.
I'll start with diversity. So right now, as Kara alluded to, more than 90% of genomic studies worldwide start with European ancestry individuals. I hope in 10 years we see that's not the case. I hope it's much more reflective. Next, I'll go to discovery. So based on more diversification on genomic studies, 2/3 of the genes, we don't really know what they do out there in terms of human phenotypes. And I think with the diversification and increasing and international collaboration, we will yield towards understanding what some of those mean. I think it will mean some diseases that we didn't have names for. I think it will yield some protective things we don't understand today that we'll be able to do. Implementation. Right now we have a huge gap of science between discovery and implementation. And I'm hopeful that programs like we have prioritized returning results directly to participants to take to their providers. I hope things like that become more routine, and I hope we're able to translate and demystify things like genomics and all the other kind of omics that we're going to be generating, and how we can get that into the clinic in ways that affect real people's lives. And then the last one I'll mention quickly is trust. I think we have a huge trust gap in this country and in other places of the world in science, and there's lots of things in there. I really hope we're making progress in that, because that will be required to move science forward into the coming decades.
Okay. We're running low on time, so quickly read.
I'll keep it pithy. I guess for oncology treatments in the next 5 years, my prediction would be the expansion of new therapies into larger indications. So what I mean by that is, when the way a lot of these companies are structured is to go after something that is a relatively lower hanging fruit when you're taking a massive scientific risk. And you saw this with maybe some of you saw a company called Vertex got the first gene therapy for sickle cell anemia approved by the FDA a few months ago. This was the result of 20 years of work, and it's amazing. Yet, if you were going to make a company doing that, you'd kind of want to go after sickle cell. It's a monogenic disorder. You knock out one, and you basically cure the disease. It's absolutely amazing. Yet, the translation of that into other non-monogenic disorders is where I think the next, say, 10 years are going to go. And that's going to mean everything from gene therapy, possibly some vaccine trials that we're looking at that are very cool right now, a lot of next-gen immunotherapy and epigenetic therapy. And instead of just going towards the areas that, it'll absolutely work if you can kind of get the science right, you'll then kind of graduate on to the next levels of seeing what this could actually look like in a much broader population where, many more people are burdened by disease.
And Catherine, bring us home.
I predict, we know that the cost of a human genome is now down around $100. It's going to become part of standard of care for everyone. It will become part of our medical record. As Josh has said, do it once, use it often. I think that's really going to build a culture of prevention, but most importantly, targeted therapies, that goal we all have in terms of precision medicine, so that the treatment that you have is tailored to you, and we remove the trial and error from treatment, so people are getting the right intervention or the right treatment first time.
Okay. Thank you so much, everyone, and thank you all for coming and sticking around. I appreciate it.